The government is enlisting 13 different departments for research and development in the event of a solar storm that could wipe out the use of modern technology. Experts constantly monitor space weather. High activity from our sun generates powerful solar flares, which are intense bursts of radiation, and can disrupt GPS and communication signals if they reach Earth. But the biggest threats are coronal mass ejections. CMEs are huge eruptions that send out bursts of solar plasma into space at unfathomable amounts of speed. CMEs that hit Earth could spark geomagnetic storms, wiping out power grids and leaving us in the dark. In March 1989, a CME caused a blackout in Quebec. Over 6 million people were without power for 9 hours. But the worst CME that ever occurred was in 1859. Known as the Carrington event, it was 3 times more powerful than what struck Quebec. It started fires and shortened out telegraph wires in the US and Europe. NASA revealed that the Earth narrowly avoided a Carrington-level CME in 2012. Experts say if it would have struck us, it would have cost over $2 trillion in damages. NASA says there's a 12% chance that the Earth will get struck with an extreme solar storm within the next 10 years.
The Sun is a colossal fireball, 330,000 times bigger than Earth. It's the source of all energy and life on Earth. But what's happening at the center of the Sun? Our Sun has no solid surface. It's made of hydrogen and helium. The Sun's huge mass generates massive gravitational forces, so strong it keeps all the planets in their orbits. Gravity creates astronomical temperatures and pressures at the Sun's core. Hydrogen atoms ionize and fuse. Nuclear reactions, millions of times more powerful than atomic weapons, fire the Sun's core. Super-dense hydrogen plasma at 15 million degrees Celsius spins constantly. It's the hottest thing in the entire solar system. The Sun's core converts 300 million metric tons of hydrogen into helium every second. The hydrogen is slowly getting used up, and the Sun is aging. Today, the Sun has enough gas to last about 5 billion years. But one day, the Sun's fuel will run out, and its core will stop working.
Sunspots are a really interesting phenomenon on the Sun. They're areas of strong magnetic field, and magnetic field is probably the most interesting aspect of physics that we're going to get out of the Sun. Maybe I shouldn't have said that because there's also nuclear physics at the core, but at least for my research, the magnetic field is the most interesting thing. And how that magnetic field is generated, how it evolves, how it changes with time, and the kinds of physical processes that occur in the magnetic field are what we're interested in, and the sunspot is right there at the surface. What we're seeing there is the effect of the magnetic field on the photosphere. Now, what we're pretty sure is happening is that the magnetic field is reducing the effectiveness of convection, the transfer of energy from below the atmosphere to the top of the atmosphere. And what happens is the magnetic field reduces the convection, makes it so that sunspot's not so hot, so it looks cooler, so it looks dark. Now that sunspot is actually hot. It's 4,000 degrees instead of 5,000 degrees. But it's like looking at a faint light bulb next to a bright light bulb. The faint light bulb doesn't look bright just because the bright light bulb is there. You take the bright light bulb away, the faint light bulb looks bright. Sunspots are the same way. It's surrounded by hotter material, so it looks dark. But if you took the hotter material away, it would still be bright.
Scientists estimate that if humans are still around in 5 billion years, they will have been forced to leave planet Earth a long time ago. For our solar system, though, it's been a pretty quiet 5 billion years. But that's all about to change. Things are getting real. Fast. Our yellow sun has run out of hydrogen to burn and started to run on helium instead. Our sun was an average yellow star, but now it's growing up. It's becoming a red giant, expanding rapidly, up to 100 times its current size. This affects the entire solar system. It's very bad news if you're one of the inner planets, Mercury, Venus, Earth, or Mars. The rapidly expanding sun begins to burn the inner planets. Mercury and Venus would be completely destroyed, melted and sucked into the rapidly expanding sun. Earth might survive, but not life as we know it. For the last 3 billion years, the sun has been getting hotter and hotter. It's so hot that our oceans have already boiled off. As the surface of the giant red sun gets closer and closer, the Earth heats up and magma bubbles up to the surface. More and more volcanoes are born, turning the Earth into a fiery wasteland. The heat will make Earth and Mars uninhabitable. As our Earth heats up and tectonic plates shift, fault lines spew out oceans of magma. Our blue planet turns red. But we've got 1 billion years to figure that out.
The Sun, the heart of our solar system, is a yellow dwarf star, a hot ball of glowing gases. Its gravity holds the solar system together, keeping everything from the biggest planets to the smallest particles of debris in its orbit. The Parker Solar Probe is going to be the first piece of human engineering that will fly less than 4 million miles above the surface of the Sun, directly through its blazing hot atmosphere. It's going to actually touch the Sun's corona. It'll be cool. Actually, it won't be cool. It'll be hot. This craft will face heat and radiation like no spacecraft before. It's not a journey that any human can make, but let's imagine for a second. What if you fell into the Sun? What would you see, experience, and finally, what would happen to you while passing through the Sun's layers? This is Googleplex, and here is what would happen if you fell into the Sun. Greek myths are hardly a realistic lens through which to view the world, but the tragedy of Icarus is a lesson that's true in any context. If you get too close to the Sun, you will die. There are no exceptions to this rule. But how close could a person get to the Sun, realistically, before burning up? The most obvious problems are the heat from the Sun and the radiation it emits. The technology in our current spacesuits really isn't designed to withstand deep space. A standard spacesuit will protect an astronaut by temperatures of up to 248 degrees Fahrenheit. Still great in most instances, but extremely poor for trying to touch the Sun. The Sun is about 93 million miles away from Earth, and it's at about 3 million miles from the surface that temperatures would scorch up to above 248 degrees Fahrenheit. Relatively speaking, this is still pretty close. It would then be a matter of time before the astronaut died. Above 248 degrees, the suit would transform into a close-fitting sauna. The temperature would climb above 125 degrees Fahrenheit, and the person would become dehydrated and pass out, eventually dying of heat stroke. But let's assume that your spacesuit is made of hypothetical compound that can survive maximum temperatures of the Sun. Your brand new sci-fi movie suit would take you all the way down to the Sun's core and would protect you from the destructive environment that the Sun has to offer, such as the huge temperatures, lack of oxygen, deadly radiation, and its enormous pressure. No need to worry about oxygen when you're about to go through one of the Sun's layers. At this point, you approach the corona, the outermost region of the Sun, starting out at 2,100 kilometers above the surface and extending out to some 5 million kilometers. Oddly, however, unlike the Earth, where the temperature of the atmosphere decreases with height, the corona is actually by far the hottest part of the Sun, where temperatures go up to a few million degrees Fahrenheit. Why this is the case is still somewhat of a stellar mystery. Certainly, if you are gradually falling and made it to this point, the temperature is already absurd, and the radiation too. If not for your super cool science fiction spacesuit, you'd be already dead. But what if you were in a regular spacesuit? What would happen then? Well, first things first, you would disintegrate. At this temperature, most of the molecules that make up our bodies could not even survive. They would break apart, leaving only loose atoms. And then temperature is enough to vaporize everything you've got, a different color for each element present in your body. But even that won't be seen because of the already well-lit spectrum of the sun. You would be turned into plasma, the fourth state of matter, just charged particles, and dispersed by the magnetic fields and solar winds. But let's return to our special science fiction spacesuit and continue our journey to the sun. After a very long time of falling, as you pass through the corona, the temperature would have dropped to 7,800 degrees Fahrenheit, and you would be within the chromosphere. This layer of the sun is located between 400 kilometers and 2,100 kilometers above the solar surface. The chromosphere has temperatures around 4,000 degrees Kelvin at the base and 8,000 degrees Kelvin at the top. It emits a reddish glow as superheated hydrogen burns off, but the red rim can only be seen during a total solar eclipse. At other times, light from the chromosphere is usually too weak to be seen. The chromosphere may play a role in conducting heat from the interior of the sun to its outermost layer, the corona. Because the gravity of the sun is so strong, you would be descending roughly 28 times faster than if you were falling towards Earth. And in no time, you would reach the lowest layer of the sun's atmosphere, photosphere. It is about 400 kilometers thick. This layer is where the sun's energy is released as light. Because of the distance from the sun to Earth, light reaches our planet in about 8 minutes. Here you would be faced with temperatures exceeding 10,000 degrees Fahrenheit. The photosphere is marked by bright, bubbling granules of plasma and darker, cooler sunspots, which emerge when the sun's magnetic field breaks through the surface. As soon as you reach the sun itself, you would sink. The gravity on the surface is 28 times that of Earth. The temperature is about 6,000 degrees Celsius. Humans can't survive 28 Gs for long. But let's carry on. There's no solid surface, just like there's no surface to Uranus. The sun's density is 1.4 times that of water. So you would be sucked inside, kind of. Except that there are convection currents. If you happen to be just above one, you might be kept close to the surface. But finally, the eddies would entrain you sideways until you came to a downdraft that would take you downwards. Eventually, you, not me, I'm out of there, would cycle between two layers in a convection cell, moving you up and down, above and below the depth where the density of the gas is the same as the density of your body. But what if your sci-fi spacesuit would be able to help you to dive even deeper, where you would eventually reach the core? Unsurprisingly, no one would survive a stroll on the hot ball of plasma. Gravitational attraction here produces immense pressure and temperature, which can reach more than 27 million degrees Fahrenheit. Hydrogen atoms get compressed and fused together, creating helium. This process is called nuclear fusion. This would be the final stage of your journey. Sorry, but there would be no coming back except if you have a teleportation device, but that's a story for another video. Conclusion? The sun is hot. So I guess there's one thing for sure about all of this. You're going to need some sunscreen. I really hope you enjoyed this video, and if you did, then hit the like button and subscribe to Googleplex for much more to come. Thank you so much for watching, and I'll see you soon.
Set the controls for the heart of the sun. In the summer of 2018, the Parker Solar Probe will lift off from Earth. It will spend the next 7 years spiraling inward to the center of the solar system. The Parker Probe will be the first spacecraft to touch our star, or any star. It will brush through the halo of hot gases that form the sun's outer atmosphere, the corona. The surface of the sun looks placid to our eyes, but it is pierced and roiled by strong magnetic fields. The fields trap gas blowing off the sun and lift it into glowing arcs and streamers. Scientists don't understand how the corona works, or why it's hundreds of times hotter than the surface of the sun. The Parker probe will pass closer to the sun than any mission before it. To get that close, the spacecraft will make 7 flybys of Venus over 7 years, gradually tightening its elliptical orbit and shifting it closer and closer to the sun. A high-tech heat shield will protect the probe from the punishing radiation and heat of the corona. But within the shield's shadow, the spacecraft instruments will operate at a comfortable room temperature. As the probe passes close to the sun, it will briefly become the fastest machine ever built by humans, zipping along at a brisk 430,000 miles per hour. The Parker probe is the first NASA spacecraft to be named after a living person. Eugene Parker is an astrophysicist at the University of Chicago. In 1958, he suggested that the sun radiates a constant and intense stream of charged particles. He called it the solar wind. This wind pushes out comet tails and makes the long streamers seen in solar eclipses. With the Parker Solar Probe, scientists hope to learn more about the sun's turbulent corona, how it accelerates particles, and how it flings huge clouds of fiery gas outward across space. Huge waves of magnetized gas are called coronal mass ejections. If Earth gets in the way of one of these storms, it could be bad news. Our planet is protected by its own magnetic field, but a direct hit from one of these galloping clouds of particles and radiation could disrupt satellites and force astronauts in the space station to take shelter. In 1859, a powerful storm called the Carrington event produced auroras as far south as Cuba. A solar storm of that size today could cripple satellites and power grids around the world. If successful, the Parker probe's mission to touch the sun may explain how solar storms form. Scientists hope it might teach us how to predict coronal outbursts more accurately and learn how to endure them. We've always depended on the kindness of a star, here on a planet riding the gentle fringe of barely calculable forces. Living with a star is not easy.
Traveling through the sun's blazing hot atmosphere, NASA's Parker Solar Probe has sent back a complex, close-up view of our star. The spacecraft confirmed that our picture of the sun from Earth is deceptively simple. Parker is the closest spacecraft to the sun, meaning we now have never-before-seen details about the solar wind and solar energetic particles. Solar energetic particles are high-energy particles that can endanger both astronauts and satellites in space. The solar wind is the continuous outflow of particles and magnetic field from the sun. Both speed out, filling up space and affecting space weather throughout our solar system. For the first time ever, we were able to go to the source of the solar wind and solar particles. Here are 5 features Parker saw. We've long known that space is full of cosmic dust. We can even see the dust from Earth because it reflects sunlight. Parker saw evidence that the dust stops at an estimated 3.5 million miles from the sun. As the dust gets closer, the sun vaporizes it, creating a dust-free zone surrounding the star. At Earth, it appears that the magnetic field lines flow evenly out from the sun, but Parker saw them behave in a surprising way. The magnetic field lines flip in a whip-like motion, turning 180 degrees around in a matter of seconds. These switchbacks came in clusters and were timed with fast-moving clumps of plasma in the solar wind. Scientists have long wondered if the solar wind is generated as a continuous flow or in spurts. We now see evidence that the solar wind has rough, irregular texture. The plasma within it also seems to lack an orderly sense of direction. Some clumps of solar material fire out into space, while others fall back toward the sun. These clumps may be distorting the magnetic field, causing the switchbacks.
They may also be an indicator of what the solar wind looks like in its early stages after its birth on the Sun. Parker found a transition point in the solar wind. The corona is the Sun's faint, outermost layer that transitions to the solar wind. Before Parker, scientists knew that the corona rotates with the visible surface below it, but they didn't know how, or where, the solar wind switched to flowing straight by the time it reaches Earth. Parker has finally spotted signs of this transition, and the changeover happened significantly farther out than expected. Although the Sun has been very quiet over the first 2 orbits, Parker observed several tiny bursts of solar energetic particles. While these events have been seen before, never ones this small. The fast-moving particles from these modest bursts spread out as they move from the Sun, making them undetectable from Earth. Without Parker's front row seat, we would never know that the Sun is regularly producing these small-scale events. Fast-moving particles are a source of dangerous radiation. The more we learn about these eruptions, the better we can protect our technology and astronauts. Parker still has more work to do, but it's already helping us see our star in a whole new light.